Hello and welcome to Under the Microscope, a real scientist nano podcast where you meet a new materials and nanoscientist with every episode. In every episode, Pranoti, who is your host, which is me, hello, I ask questions to our guests about their science, about their current research, about the project that they're most proud of, their scientific journey, and much, much more. I am very nosy, so I do ask a lot of questions to get some spontaneous answers out from our guests. Do check out our Twitter account as well, Real Scientist Nano, which is real_sci_nano. Also, do consider leaving us a review, sharing this podcast with your friends, going to the settings and hitting the download button, because that helps us with reaching wider audience. Thank you and enjoy the episode. Abstract submission for the 6th Nanoscientific Forum Europe 2023 is now open. Join this European SPM meeting and be part of exciting talks from the nanoresearch field, practical hands-on sessions, and a thrilling social program in Barcelona's Flair, hosted by ICFO, Barcelona, Spain. See you in Barcelona in September 2023. Hi everyone, my name is Pranoti. I am your host of the Under the Microscope podcast, and today we have with us someone really amazing, and that's George Mihailescu, who is a PhD student or PhD researcher at the University College Dublin in Ireland. So, hi George, how are you?
Hello, hi, nice to meet you. Thanks for having me on today. I'm very excited.
Very excited to have you.
Very excited.
Dig into your science. So let's get cracking. So please, can you explain your research to us in super simple words?
Yeah, of course. So in my work, I look at miniaturized technologies and ways of carefully controlling them or manipulating them to perform some sort of intended task. So by miniaturized technology, I just mean a system that's on the nanoscale and that's governed by the laws of quantum mechanics. And the type of tasks that we're interested in are things like computation or sensing. So that's basically the gist of it.
Okay, so quantum, computation, sensing. So you're working with futuristic, you're basically shaping our future technologies. Is that a fair assumption?
Yeah, I think that's a very complimentary way of putting it. But yeah, the quantum technologies too, there's a lot of investment in it currently, and many people are interested in this domain. And there's a lot of efforts going towards developing quantum enhanced devices at the moment.
Okay, all right. That's really interesting. So how did you get into this this field? Like, what has your journey been like? I mean, I'm sure as a 5-year-old child, George did not think that he wants to be a PhD student at University College Dublin and working with the quantum technology at miniature level. So how did that come about?
Yeah, so actually 5-year-old George was very interested in science. I was always interested in science broadly, like from a very young age. I think most kids are like, you start off and it's like, oh my God, dinosaurs are so cool. You look at the stars and you're like, whoa, the stars are so cool. They're so pretty. How does that work? And then there's all these TV shows and, they talk about black holes and time travel and, living forever, superpowers and so on. So, that was always kind of an interest of mine. But I guess how it came to be, obviously at that age, I didn't know what a PhD researcher was, or, to be a scientist basically means, you're doing research, which means you're in academia typically. So the way that kind of started was, I think I had a pretty basic and normal career trajectory in that sense, that I did a bachelor's degree in Dublin City University in physics with biomedical sciences. So the reason why I chose that topic was, as I mentioned, I was generally very interested in science, and I didn't want to lose I knew I wanted to focus on physics, but I didn't want to lose the biology and the chemistry kind of elements. So I thought that this degree was the one for me. And then in the latter stages of my bachelor's program, I kind of realized that I was more interested in computation and mathematics. So we're really lucky here in Ireland because when you're in your final year of your 4-year program, you usually do a research project for that year. And mine was in machine learning for quantum many-body systems, which I really enjoyed. And it touched on all the pieces that I was really interested in, like computation, mathematics. And that kind of gave me the idea, like, okay, I think research is really the thing for me. Maybe I'll go into academia, but I wasn't sure because, the industry is calling, and academia, I've heard at the time, right, was a big commitment that requires financial sacrifices, emotional sacrifices. So I thought maybe to make a more informed decision, I should do a master's program, which could help me. So that's what I did. I enrolled this time in University College Dublin to study applied mathematics and theoretical physics. So yeah, once again, in my master's, I had the chance to do another research project. This time I linked up with a professor called Dr. Steve Campbell. So he's an expert in quantum information theory and quantum thermodynamics. And what we were working on was a project on charging quantum batteries. So, okay, I know that sounds kind of like, yeah, okay, so like, what is a battery? So a battery is like a device that stores energy, and then you use this stored energy to do some work, like to do some task. So then, yeah, a quantum battery is just the quantum analog of that. So you have a quantum system, and you store energy in the energy levels or the coherences of that quantum system, and that allows you to extract or do work from them. And then the charging element that I was looking at, so let's say you have some initial state, but you want to manipulate that state then to go from where it is to a higher energy state, because that means that your battery has more energy stored so you can extract more work. So that makes sense, right? So that's the kind of thing that I was looking at. So I thought that was very, very interesting, very, very cool. And then I had the good fortune that my master's project was being graded by this other professor named Dr. Andrew Mitchell. And he's an expert in like strongly correlated electrons and Kondo physics. So while he was correcting my thesis, in the background, there was a collaboration forming between him and Steve and this third party called Equal One Labs, which is a startup company. And they're like trying to develop a quantum computing platform that's based off of CMOS technology. So CMOS, what that means, so they're CMOS stands for complementary metal oxide semiconductors. So these are like highly scalable technologies that exist in commercial and modern computers and other type of electronic devices. And what they're interested in is seeing the quantumness of these kind of systems, and whether they can exploit them to like create quantum computation. So kind of putting together, Steve's expertise and Andrew's expertise and their expertise, they were like, let's work together and see what we can do with our system. How can we make our system work better? And I just happened to be at the right place at the right time, being graded by the right people, being supervised by the right people. And the opportunity came up, and then I was like, yes, please. And like that kind of brings me to where I am today, I guess.
Okay, wow. Okay. So from being a 5-year-old interested in dinosaurs and all the other stuff to now, I have so many questions. Let's go one by one. So you mentioned your master's thesis was about quantum batteries. So what is this, like a theoretical concept, or does it actually exist? So can I run my car, or can I charge my phone, or can I have a quantum battery in my phone? And will that be better than the current, like probably lithium battery that I have in my phone? I have no idea about the quantum world. My expertise lies in 2D materials and the basics of it, fabrication and like and all of that. So the quantum world, I know a little bit, but I want to learn from the expert here. So quantum batteries, what is that, like imagination, or is that a theoretical, or is that a practical thing?
So in principle, the theoretical models that we have, they're representative of actual physical systems that you can develop in the lab, like things like maybe you can envision a quantum dot or electron, something that has different energy levels that you can manipulate and store energy in. Now, do they exist right now? Are they being developed in the lab? To be honest, I'm not sure if they actually are being developed in the lab, but I think one of the biggest issues with quantum batteries or just quantum technologies in general is that you really have to have a lot of control over them. So right now, they kind of work best at cryogenic temperatures where temperature fluctuations can't spoil the quantumness of them, which is what we want to exploit, which gives them maybe potentially, in some cases, advantages over a normal battery or a normal computer. So will it be in your phone tomorrow? Probably not, because your phone, it's hot in your pocket. When you put your phone underneath your pillow, it's hot. When you drop your phone, that's just going to spoil the quantum state. So will they exist like today? Probably not today, but in the future, I don't see why not, because there's so many people working on creating working quantum devices.
Okay, that sounds very similar to. So recently, I had a conversation with someone actually in the UK. Her name is Anna Polovsky, and she worked on, and this was like a few years ago. She worked on hydrogen fuel cells, and I asked her the same questions as like, is it possible to get it tomorrow, or where are we in terms of the research? And she also mentioned that at cryogenic temperatures, or so it's the hydrogen fuel cells, they work quite well, but at room temperature we are not there yet, but in the future, hopefully soon, this will happen. Okay, interesting. So when we talk about the quantum batteries, what kind of materials are we talking about here? What kind of materials, even at cryogenic temperature? And just for anyone who is listening and who does not know what cryogenic temperatures are basically 0 to 4 Kelvin, and I think 1 Kelvin is 1 degree Celsius is 273 Kelvin. Oh wow, it's been a long time since I was.
I think 0 is 273, right?
Yes, 0 degree Celsius is 273 Kelvin. So when we are saying -4, how much is that? Minus 269 degrees Celsius.
Yeah, which is a little bit cold. I mean, a little bit.
A little, yeah. I mean, yeah, just a little bit cold. Can we put our finger in there? No, we can't. So which materials are we talking about here at minus 269 degrees Celsius?
So specifically, I guess the type of models that we envision, or that I envisioned as a theoretical physicist, we have like these simplified, basically spin systems is what I was playing around with. So a spin system, you can think of something that can point like either up or down, like this kind of system. In terms of like a material, to be completely honest with you, I didn't think that far ahead of like what kind of material. We were thinking about, very simple models of qubits, basically, where a qubit is like a quantum bit of information. So we were thinking about those kind of systems. But in terms of the actual physical manifestation of this, that was not something I considered. But maybe there are works that like consider an actual material. I'm sure there is, but it's been a while since I worked with them. So I couldn't cite it off the top of my head, but that's a good question. But I wish I had the answer to.
Yeah, that's absolutely fine. That brings me to the next question. So your current research, together with this CMOS interested startup, let's talk a bit about CMOS. So CMOS, is that the circuit system that we have in our phones or our electronics? Or That's the one that we have, right? Okay, alrighty. So that brings to my mind these advertisements I saw of Intel, like quantum chip and quantum computing power and bari da da. So it seems like, at least from that advertisement, that Intel is already doing that. So are they doing it? What is the truth there? And if they're doing it, why does a startup in Ireland want to compete or venture into a field where there are already giants like Intel, AMD, and Darida? Tell
Yeah,
me.
that's a really good question. I think that there's a lot of different facets to that question. So maybe I'll try to break them down.
Please.
So yeah, there's many companies, like big companies. There's Google, there's Microsoft, there's Intel, there's IBM, right?
Meta.
Yeah, they're all investing in quantum computing, quantum devices, and they're all kind of looking at different physical implementations that each poses kind of um, potential advantages over the other, right? And they have a lot of money, and they have a lot of resources that they can devote to that. So then, how, is there space for a startup company or for any startup company to come into this space and make a contribution? I think yes. So there's many quantum computing startups, and some of them focus on hardware.
Uh-huh.
So that means either a different type of implementation of their qubits or different kind of implementations. Whereas other companies they take the approach of, okay, so there's big fish working on the hardware. Maybe we can contribute by working on the software. So once you have these qubits, how do you actually translate, those quantum bits of information and write code with them to actually do something useful, right? So there's companies who are, working on that domain. So there's like various different approaches. Now, where does Equal One stand in all of this? So, okay, from what I can tell, again, so I'm being funded by them. I'm not directly one of their employees, but what I can tell and say about them is that they have this really nice idea that, okay, CMOS is this technology that's ubiquitous in today's society. It's in most computers and phones, etc. So the idea is we can make these. They're relatively cheap compared to other kind of platforms. That's good. So they're scalable. So what this means is if we can, they're very small. They're at the nanoscale anyway. So maybe there's something quantum going on down there because they're at that scale. Why not? So if we can leverage this quantumness to actually do the same type of tasks that the other companies do, but we have a system that's scalable and that can work at, maybe they can work at actual day-to-day temperatures too. So this allows us to, okay, maybe they're the quantumness of them isn't as good. Maybe they're more subject to noise than the other systems are, right? But if you have more of them, maybe you can compensate by, suppressing errors or doing something like that. So that's the kind of approach that they're taking, but they're just not limited to just that. They're also looking at things like, applications of like the device. For example, I think they have this interesting paper where they explore quantum algorithms for GPS tracking or something like this. So they do a lot. That's not something I know about, to be honest, but they do a lot of different things. So they're not just focused on the hardware. But I think their approach is very interesting and promising. I think all approaches should be investigated because at the end of the day, you don't know which one will work, and so I think it's good. A bit of competition never hurt anyone.
Yeah, absolutely. Thank you for answering and helping me and our listeners understand this whole fascinating world. So, my next question would be, I mean, now that we have you on the podcast, what is the relation, and is there a relation, and if there is, what is the relation between quantum computing and chat GPT or Bard AI?
Okay, I guess the relationship between, so ChatGPT is powered by artificial intelligence or machine learning, right?
Yeah.
And the idea is that if you have kind of a quantum computation platform, right, you are able to perform certain types of computational tasks faster, or yeah, you can compute, you can perform them faster. Certain tasks become tractable that before were intractable. You can access a data set that's really big. So let's say you have terabytes and terabytes of data, you can access that potentially faster too than you could in like a traditional kind of sense, right? So the idea is, I guess, that you can exploit these speed ups to train your models faster, to maybe train your models better, although I don't know too much about that. But I think those are the general ideas there. So if you have, you know, there's currently in today's society where generating like copious amounts of data. So using that data, you know, is to train models or to perform. And there's like supervised machine learning, there's unsupervised machine learning, where you kind of like you just look through the data and you're kind of trying to find trends, right? That's the idea behind unsupervised machine learning. So, but that's very time consuming, right? And it can take many weeks to train a model, and then maybe you train your model and you find out that, oh, I should have tweaked this parameter a little bit better to get a better improvement in how it matches, right? And then you have to wait another few weeks, and then this process repeats itself. So I guess the idea is that if you had a potential speed up in the accessibility or the way in which you can learn, then you can do all these things faster, which ultimately results in better ChatGPT coming sooner, and then, yeah.
Right. Yeah, basically making these kinds of, not technologies, bots, what do we call them? Features? No,
Like
applications.
ChatGPT? Yeah,
Yeah,
applications, I guess. Yeah, applications.
making them faster and better in terms of the quality of responses, so on and so forth. Okay, that sounds cool. Okay.
Yeah.
My God, we are living in fascinating times, I have to say. And yeah, oh my God, wow, I have so many questions for you. But now I want to ask you a very mean question, and that is, from all the projects that you have been part of, do you have one project that you're most proud of, or the research experience? And if you have one, and I'm sure you do, could you explain it to us in simple words in the section we call In Other Words?
Yeah, so I think the work or the project that I'm most proud of is our most recent work, which is also the first project that I did as a PhD researcher, where we ask a very simple question. We just ask, okay, what happens if we use a quantum system as a temperature probe or a thermometer for a quantum sample? Okay, so just to unpack that very loaded sentence a little bit, let's think about a thermometer, right? So when we think about thermometers, when we imagine them, we typically have this picture in our head of like a glass tube that has some markings on it, and then there's a liquid in this glass tube, right? So that's what we typically envision. And then let's say there's a sample, and we want to know what the temperature of that sample is. So then we get our thermometer, and then we just stick it in to the sample. Then what we do is we need to wait a little bit of time so that the thermometer and the sample go in equilibrium with one another. So we can just go for a coffee, we can chill, relax, and then we come back after a period of time. And then we're like, okay, I think it's time to measure the temperature. So then we squat down, and then we look at the glass tube, and then one of two things can happen. We're like, okay, either the liquid will go higher than the position it was originally, and that's because the sample is hotter than room temperature, which made the liquid expand, or the liquid can go lower than it was originally, and that's because the temperature of the sample is colder than the temperature of the room. So then we have the very difficult task of looking at where the liquid is and which marking it aligns with, and then we're like, yes, it's this temperature, it's temperature X. Okay. So then why are people interested in quantum thermometers? Well, the literature tells us that if you use a quantum thermometer, you can make the most precise or accurate temperature measurements that you possibly can, right? So this is really important. And I'll give an example why this is important. So imagine we have an experiment or we have a device. And what we want to do is this device or experiment will only work in a very restricted and small temperature regime, right? So if you're too hot, the experiment or device won't work. If you're too cold, the experiment and device won't work. You have to be exactly in that regime, right? So what you need to do then is you need to either heat up the room or cool it down to make the thing work, right? But the only way you can do that is by measuring the temperature. But if you have a thermometer that's not so good, then it's going to be really hard for you to get the temperature to just that sweet spot, if not impossible. So then what you need to do is very, very accurately and precisely be able to measure the temperature, right? So this is why it's an important task. So then what we say is, okay, we know that quantum thermometers offer the best precision. So what happens when we put that in a quantum sample? We want to measure temperature with quantum sample. And this is a very interesting question because you have a lot of kind of non-trivial phenomena going on. There's correlations that build up between the sample and the temperature probe. There's entanglement and quantum correlations all going on, which kind of fuzzes everything up. And you have to be very careful of what's going on, but it's also very exciting. So then what we found in this work was that, okay, if you do temperature measurements in this kind of setting, you have a very robust thermometer. So for example, we look at different types of samples. So we look at graphene or twisted bilayer graphene and metals. And we see that in each case, we have these very well-defined characteristic thermometric response. And what this tells us is that, okay, we have a very reliable and robust thermometer that works in all these different samples in a reliable way, which is very important because we want thermometers that, that the way they work is well defined, because if they're not, then it's hard to characterize what's going on. What is the temperature, So this was very, very interesting, and it was my first project, so I keep it close to my heart. So I was very happy with that. Yeah.
Okay. Wow. This is really interesting. I love quantum thermometers. The idea of it. I mean, this makes a lot of sense, and I can understand why you picked this as like one of the projects that you're most proud of. So just to follow that concept of it, the quantum thermometers. So it's not just limited. I mean, I would say it's not just limited in the lab, right? When we are cooking, for example, and if broccoli needs to be heated at, I don't know, 39.4 degrees Celsius. I don't know. What do I know? To taste in a certain way or to have certain kind of texture, then we need to have this temperature precision, be able to measure and also to sense this kind of temperature and to display this kind of temperature, right? Is that realistic? Like real life example, like one of the potential applications for your quantum thermometers?
So I think the most exciting applications are, for example, okay, like I mentioned at the start when we started talking, is that we would like to have working quantum computers. But one of the biggest issues for quantum devices in general is that they're very subject to noise or and a source of noise is thermal fluctuation. So if there's a temperature fluctuation, it can destroy the state that you want to use that potentially is better than a normal state, right? Let's say. Right. So what you need to do is you have to know very well what temperature your device is operating at, because that way you can eliminate sources of noise, or oh, I'm in this temperature regime. It's not going to work very well. Right. But then there's also other applications, for example, this is not something that I know too much about, but I think is really exciting. There's people have recently measured, what have they measured?
A lot.
They've measured a lot of things, but so going forward, you want to measure magnetic fields or gravity or something, you can use these quantum sensors for things like that. So I think it's very, very nice. But in terms of for your broccoli, I don't know if you'd want to pay that much money to know, when if your broccoli is going to taste that good. Maybe there's better uses than for your broccoli. Maybe for carrots.
For carrots, yeah, definitely. I'm not a fan of mushy carrots. They have to be like perfect temperature or perfect texture, so to say.
Or for chicken.
I'm a vegetarian.
Oh, okay.
But yeah, no, that was just me trying to bring the quantum thermometers in real life. And of course, we are far away. There are a lot of other sophisticated applications at this point for quantum technologies, including the quantum thermometer, of course. But yeah, I hope that at some point it does tell me what the temperature. Actually, it doesn't tell me what the temperature of my broccoli is. It just makes it for me, so it tells the system that, yeah, well, wishful thinking. But I mean, now that we were talking about this, and with the temperature and everything, and the noise being like the thermal or temperature changes causing the thermal noise, is it easier to use the quantum technology, or rather, let me put it this way: is it easier to apply quantum technologies in space? So, like using a quantum thermometer in space rather than on Earth, because, well, the temperatures are lower, the space, and I'm assuming the noise is less than compared to Earth. I don't know.
I think that's a really good question. I'm going to give an educated guess here and say, okay, maybe you're reducing the temperature fluctuations, right? That's good. But there's other types of radiation and noise sources, right? Like there's so maybe they can, also destroy the coherence of the states. So, I mean, I see, and I think that you're probably right in that sense, that maybe it would be easier in space. But I do think that there's other types of noise sources that we need to shield against that maybe we don't even know of, so I would say we currently have like the nice atmosphere that shields us from other types of radiation, and in the lab we can create these I think in a lab we can create environments that are more stable than in space, or I think.
Yeah.
So I think
you can control the lab environment to a higher degree than in space, because we just live.
We can't control space.
Yeah, absolutely. Yeah. Absolutely. Awesome. This can go on and on forever, I feel like. But I mean, let me take you a bit away from just the research aspect of being a scientist. So what else do you like about being a scientist, being a PhD student at this point, other than the science? Because I see that you're like into science, but what else do you like?
So I think one of the really nice things about doing research is that, when you're doing the research, it's all well and good. You're learning, you're thinking about new ideas, and that's very fun and it's very enjoyable. Right. But on that journey of learning, by reading papers or thinking of new ideas, quite often you communicate with people. You communicate with people in your lab. You communicate from people all over the world, right? And you're brought together by, you don't know these people, they're on different sides of the world, but you're brought together by something that you have an interest in and that you're both very passionate about. And I think that's very nice. And quite often then you have conversations, you might travel to meet them and work on something, or they might come over to you. And you also travel to conferences and stuff like this. So I think that like the fact that you get to see how other people think is really nice. The fact that you get to meet new people and the fact that you get to travel to new places, I think it's like a real life adventure, and I think that's really, really cool.
Yeah, that's a good point. Yeah, absolutely. I remember this. Oh, I should, every time I speak with a scientist, I'm like, I should go back to science. What am I doing here? I should go back in the lab and be a scientist. But then, yeah, well, there are also things that don't go as expected, of course. So I hope your research experience has been wonderful, George, and I hope it will continue to be wonderful. It sounds like it has been wonderful. However, if you had 3 wishes to improve your research, what would you ask for? And I'm not promising anything here, okay? Yeah.
Okay. So if you're not promising anything, then I'll allow myself to indulge. I'd say, and the first one would be for more time. Okay. So I feel like like so there's so many levels to this. So on the first time you're doing some research, right? And you're reading something and you think this is so cool, I'm going to work on this. But then you find out, oh, there's this other thing that I should understand that would help me understand this better. And then you're like, oh, but there's this other thing that's just completely different, but is really cool. So then you start following those threads. And then when you're in those threads, you're like, oh my God, there's this other stuff and this other stuff. And that just keeps branching and branching. And then there's like just so much things that you want to learn about, that you want to work on, that it becomes like intractable. You can't possibly do it all, right? So that's very sad that you don't have enough time to do that. But then also you have other responsibilities, right? You're not just doing the research. You also have to like write papers. You have to write code. You have to debug code. You have to go to conferences. You have to correct assignments from students. You have to maybe give some tutorials. So that's all a balancing act. So I wish there was more hours in a day, there were more days in a week and so on, so that I could get to do everything that I want to do, because it's all really exciting. Yeah.
Right. So that's your first wish. Okay. You have two more. Go for it.
Oh, I have two more wishes. Oh, this is like a little genie lamp. So I think that the second one that I would wish for, I think that this is a bit of a global problem, but I think I'll speak from an Irish perspective, is that PhD stipends are like insanely small, and that when you do the money in versus money out cost analysis at the end of the month, you have more money out than you do coming in. And this isn't because PhDs in Ireland live in villas with swimming pools. It's not because we eat in Michelin-starred restaurants. It's quite the opposite. I mean, students typically live with like many people in a room, shared rooms and so on, because the stipends are so small. And the biggest issue is that, okay, there's this cost of living crisis going on. The stipends are so small. And anybody who's doing a PhD or is a PhD researcher knows that you work more hours than a 9-to-5 job. And the work that you do is important for society, but it elevates the university, because you're the one that's doing the research that elevates the status of the university. You also have teaching responsibilities that takes away the workload from the professors, which allows them to do their work, right? And then you also work a crazy amount of hours. So I don't think PhDs want to get paid in like as much as they work. I think we just want a salary that would allow us to not worry, will I have somewhere to live at the end of the month? Or who's my next roommate gonna be,
Yeah, absolutely. Oh, yes, definitely. This is like a worldwide problem, and I'm sorry to hear that that's also the case in Ireland. I really expected better from Ireland. Come on, Ireland.
Ireland.
Like, what is wrong with you? Come on. You have such bright minds and you have such amazing research institutions. Come on, pull your socks and let your PhD students at least try to have at least one Michelin star dinner every year. At least one.
At least one.
At least one. Yeah, but no, I think that's a fair, like, on a serious note, I think this is like a worldwide problem and it needs to be addressed. And I do remember that in Germany, this was addressed, or this was rather voiced, and that led to increasing the salaries a little bit, not heavily, but I mean, come on, at least the basics should be taken care of so that PhD students can focus entirely on doing the PhD, supporting the professors, mentoring the undergrads, and like tons of other responsibilities. I think that's absolutely necessary. Okay, so that's your second wish. Third and last, use it wisely.
Okay, so here I'm really going to indulge. This one might not be doable. So I'm very emotionally attached to my computer. And as I mentioned before about time, I'm writing a lot of code, so often I have to debug code. Now, the biggest issue that I have is that although my computer or my laptop is amazing, I have the worst keyboard. So it's like the worst keyboard, right? So every time I'm trying to debug my code or I'm writing a paper, like if I write a word, it always has way more letters than it's supposed to have. If I press the A key, it doesn't just give me one A, it gives me 10 A's. So that's really annoying. So I would I would wish for the same laptop, but somehow for the keyboard to be better.
Which laptop do you have? What the hell?
I have the very famous and notoriously bad keyboarded MacBook Pro, like the old ones with the touch bar that everyone hates. Yeah.
Oh my God. Oh my God. Okay, we need to talk to Steve. I need to talk to Steve and get you a better laptop or at least a better external keyboard. Do you want
Yeah.
one with lights like rainbow lights, or do you want like all red and like these gaming keyboards, or
No,
what?
so see, this is the problem, right? Because I could easily get an external keyboard, but then I just feel like I'm too far away from my computer,
Oh
from
my
my laptop. So
Oh
it's also
God.
I'm also the issue, you know. It's not just the it's me too. Neither one of us wants to change. My computer doesn't want to have a better keyboard, and I don't want to be further away from it.
Oh my God. Okay. See, George, this was your chance to
This is
ask
my
for a
chance.
better computer and better keyboard. I would have happily cut this part out for Steve specifically and sent it to him, your supervisor. Do you have one more go? Do you have like a wish, like a laptop wish or a computer wish with a perfect keyboard that you have that I can put in Steve's inbox as a wish that might come true?
um. Oh, but I already feel like I've asked for too much.
It's fine. You're not getting any of these things. Don't worry about it.
Yeah, I guess the new Macs look very nice too with the M1 chips. They look pretty cool.
Have you tested their keyboards?
Actually, I think Steve has one, and I like he seems to have no issues in the emails, so I'm assuming the keyboard is flawless.
Okay. Alrighty,
Yeah,
Steve. We are coming for you.
we
I will
are.
happily pass this message on, and I'll try to get you a new laptop or a new
Thank
keyboard.
you.
To be honest, Joyce, did you spill coffee or like
No,
milk in your
no,
keyboard?
no, no. From
No?
day one, it was like this. From day one.
Yeah? Okay.
Yeah,
All right. That's fine. Okay.
I'm not a
Steve,
spiller.
you're not a spiller, but are
No.
you like because I'm really bad with electronics. Like all my
Mm.
electronics are cracked and have dents and all over the place. Are you also are you a dropper?
So with my laptop, no. With my phone, I mean, I think dropper is too nice of a term for what I am. And the way that my phone just gets tossed around is just, yeah, yeah. So with my phone and with my laptop, it's like my baby.
Okay. Alrighty.
But I don't know what that's like because I don't have an actual baby, but I'm just assuming.
Yeah, but you have a dog, so
Yeah, same thing.
close
Yeah.
to it. Potato, potato, same thing. Sorry, not okay. Never mind. And yes, I was being subtle. I was trying to be nice with the term dropper because my electronics, if they could speak, they would say the exact same thing. That I consider more like a ball thrown at
Yes,
a
yes.
wall and
I'm the
stuff.
same.
Yeah, I mean, I don't do it on purpose, okay? It just happens.
Just happens. Yeah,
It
yeah.
just
I
happens.
agree.
Point is, Steve, George needs a new laptop with a better keyboard. He's fine with the old laptop as long as he gets a better keyboard, but that does we talked about it, we discussed his, and we came to the conclusion that we need a better laptop for for George. Excellent. Also, I just realized, Siri, I'm not talking to you. Sorry. My Apple Watch is just like, hello, what? Um, but no, this has been wonderful, George. And I just realized that this is going to be the 200th episode of Under the Microscope.
Oh,
So
wow.
you are on a.
I feel privileged.
Yeah, of course. I'm so happy that you are our 200th episode. This has been amazing. This has been so cool, George. But before I let you go, I have one last question for you, and that is,
Okay.
in addition to being featured on Under the Microscope, you are also taking over the Real Scientist Nano Twitter account. So, what can the followers expect in the week that you're taking over the account?
So I think that week I'm going to try to do a lot of different things. So you can expect to see very interesting work that's being done in UCD. So not just from me, but from the many different groups that are interested in quantum science.
Right.
So we have experts who are looking at many body physics and nanoelectronic devices. We have people working on quantum gates, all these different types of things. So I'll make sure that that research gets highlighted and featured. I'm also going, for people who are interested potentially in doing research in Ireland, I'm going to be trying to speak to some PhD students and kind of give their perspective on what it's like to do a PhD in Ireland, what their research is about. And then I'm going to do the same with postdocs, what it's like to be a postdoc in general, what it's like to be a postdoc in Ireland. And then finally, for those who are currently doing their postdoc and want to become a professor, I'll try to talk to a professor and see like how that journey like unfolded. And then I'll also try and see if I can organize and get a sneak peek into what's happening in Equal One. That could be fun. Yeah.
That's gonna be so much fun. Oh my God. Oh my God. So many cool things. I feel like you need like a month on Real Nano to get through all of these things. But no, thank you very much. This has been wonderful. And for all the listeners and watchers of this video, please follow and find George on all kinds of different social media channels, not just George, but his groups as well, on Twitter, on LinkedIn, on Instagram, and also find George on Google Scholar. The links will be in the description or in the show notes of this episode. So thank you very much, George, for talking to me. And do you want to plug anything? Do you want to acknowledge any funding agency or any collaborators? Yes. Go for it.
Okay, thank you. So I just want to say thank you to you for having me on today. And I'm very honored to be your 200th episode. That's like really amazing. Yeah. And yeah, I just want to thank, I guess, my supervisors, Dr. Steve Campbell and Dr. Andrew Mitchell, for all of their guidance. And of course, I want to thank Equal One Labs for funding this PhD project. That's really exciting. And at the interface of many different subjects.
Subjects, yeah, absolutely. We will also put a link to Eco One if there is a website. We will put the link so any and everyone who is interested can go and flood the website after listening to or watching this episode. So thank you very much, George. Looking forward to having you on Real Scientist Nano. Thank you very much. I learned a lot and this was amazing. Thank you.